Okay, ion exchange in soils is really the reason why we're here. This is the kind of the crux. It's another way to say soil fertility, in my mind at least. And so let's kind of dive into some of what we're talking about. So ion exchange is a reversible property of soil. We can think of ions as atomic or near atomic level particles that are either cations or anions. And so if it's a cation or anion, it is a depending on the charge, right? So cations are positively charged ions, anions negatively charged ions, and so these are either adsorbed or fixed to the soil in some other way, and are really important for occupying exchange sites. Okay, and so this is what we had just discussed. Cation-anion exchange in soil occurs on surfaces of soil, primarily in clay minerals, um, which make up a large, for most soils, make up a large percentage of kind of the exchange sites. But organic matter can also disproportionately make up a decent amount of exchange sites. So really, these three pieces of clay, organic matter, and roots really dictate the cation and anion exchange of soil. Okay, so our soils here in Ohio, and most soils in general that are agricultural soils, cation exchange capacity is much larger than anion exchange, and therefore it's more important. We really don't think most folks that work in kind of the industry of soils or crops or agriculture don't really even think about anion exchange, but really cation exchange is a big part of how they think about soils and manage soils. So CEC, or cation exchange capacity, is one of the most important soil chemical properties that influence plant nutrient availability, influence plant nutrient retention in soil. So it's often I would call it a fundamental or foundational property of a given soil that determines or dictates what that soil is, how nutrients cycle through soil, etc., etc. Soil CEC can be defined as the total quantity of negative surface charges on clay minerals. Okay, so the ability to attract and hold cations is really what CEC is. It's how it's defined in many ways, and so CEC includes both permanent and pH dependent charges, and so some of the charges what does that mean? That means that some of the charges, if we think back to intro soils, uh, some of the charges are permanent, they're always there regardless of pH changes, and some of the charges might flip from plus charge to a minus charge depending on the pH of that soil, the pH of the solution. So um, we can also think about anion exchange capacity, or AEC, and conversely to CEC, it's the total quantity of positive surface charges. Okay, so AEC is more important in highly weathered soils in tropical or subtropical regions. But like I said, here in Ohio, CEC is by far a more important property in what we think about. Okay. So CEC, or cation exchange capacity, indicates the ability of a soil to hold cations in their exchangeable form. It's a measure of potential of available nutrients and nutrient supply, but it's not really a measure of the true or the actual nutrient supply. That's going to depend on what cations are there and in what proportions. That's going to depend on the actual nutrient supply, of course. Okay. CEC uses a kind of a funky unit, and we often it's a milliequivalent is really the standard metric, right? So milliequivalents per 100 gram of soil is really what's used, and so a milliequivalent is a measurement of charge. Lots of times in soil tests, and we'll get into some of this a little bit later, but when we look at a soil test, it will say, percent organic matter, or part per million of calcium or phosphorus or potassium. Those are really mass it's a mass of organic matter or a mass of calcium per mass of soil. So it's a measurement of concentration. For CEC, we think charge is really more useful when discussing ion exchange, and so we use this unit accordingly. So milliequivalents per 100 gram of soil is what you'll see everywhere, except in the United States, except when you're in scientific literature. And the SI unit is centimole charge per kilogram of soil, right? And so that's this designated here, centimole charge per kilogram. Fortunately, it's one of these rare times when the kind of English or imperial unit, the 1 milliequivalent per 100 gram of soil, actually equals 1 centimole charge per kilogram. So fortunately for us, this is one time when we can, the units might be different, but the meaning and the scale of those units are the same. So those are equivalent measurements. Mentioned that soil texture strongly influences CEC, and so this is really why CEC is an important measurement, because it dictates the type or the texture of the soil. We can see really sandy soils might have CECs of 3 to 5 milliequivalents per 100 gram. Lots of ag soils in Ohio and a lot of soils in general, the vast majority of them will fall in somewhere between like a 7 or 8 to 15 up to 20. And so those are loams and silt loams. We can have soils in Ohio that are much higher than that. So, CCs of 20s to 25s are not uncommon. Those are getting into very clays and heavy clay soils. And then CCs that are above 25, maybe into the 30s or 40s, those are really going to be inorganic soils. Here in this table, it's listed into 50 and 100. 50 would be if it's above 50, it's absolutely inorganic soil. But really, in many cases, much before we get there, into the 30s or above, we're calling those organic or muck soils in general. And that is because they've got so much organic matter in there that it's really driving those CECs up, okay? So CEC of a soil is affected by the nature and quantity of clay minerals. Soils with 2-to-1 minerals have higher CECs than soil with 1-to-1 minerals. Well, what does that mean? Well, if you think back, and maybe some people, hopefully most people in this class have taken intro soils, but if you haven't, it might require a little bit of legwork to kind of catch up to some of these concepts. And we'll talk a little bit about 2-to-1 to 1-to-1 here in a second, but soils with high clay and organic matter contents typically have higher CECs, right? We just talked about that. However, not all clays are created equal. Given similar clay contents and similar organic matter contents, soils, say in the Midwest and in Ohio or in really most of the Corn Belt, can have much higher CECs than, say, soils with the same clay content, same organic matter content, say, in the Southeast. What's the difference between those two soils? Well, our soils in the Midwest have been more recently glaciated, and they're geologically younger soils than the soils in the Southeast. The Southeast, say Georgia, Florida, Alabama, have not had recent glaciation and have had a lot of weathering that's happened, okay? And so that weathering has influenced the type of clay, i.e. the mineralogy of that soil, the type of minerals in the clay and the mix of those minerals. And those have different properties, and typically the exchange capacity of those clays, those older weathered soils, is lower. So when we say 2-to-1 clays, those are what I'm referring to as more recently glaciated, more fertile soils, and 1-to-1 clays. So these would be things like alpha sols and mollisols and septosols that we would find in Ohio, in the Midwest, and these 1-to-1 clays are more oxasols and altosols that we would find in the Southeast, okay? So we're going to pick this apart, and you're just going to have to bear with me for just a few minutes while I get into some of the nitty-gritty. And I think this is, it's important really to kind of understand some of these concepts when we're talking about 2-to-1 and 1-to-1. What are we talking about? Okay, so clay structure, clay mineral, and this is greatly simplified. Mother Nature is a complex beast, but let's just talk about it from this. We've got either clay is really made up of, and this is, from Soil Science 101. You pull your Bray and Weil book, and you'll find this. But they're made up of oxygen and silicon, or they're made up of oxygen and aluminum, right? So these sheets of silicon tetrahedral sheets or aluminum octahedral sheets. Okay, so there's a silicon with 1, 2, 3, 4 oxygen, and here there's aluminum with either 6 or 8, making this octahedral sheet. Okay, and so why these three elements? Well, not surprisingly, if you look at kind of the entire composition of the Earth's crust, oxygen, aluminum, and silicon make up a large percentage of the total amount of, of Earth, right? That's, in the crust of Earth at least. And so there's a large percentage of these three things, and that's the stuff dirt is made of, soil is made of, right? So, but getting back to this idea of 1-to-1 clays versus 2-to-1 clays, that designation is a generalization for clay, and it depends on if it's 1-to-1 of these octahedral and tetrahedral, these aluminum and silicon sheets, or if it's a silicon, aluminum, silicon sheet. Okay, so again, going back, and I realize this isn't the greatest pictures of all time here, but we've got these silicon tetrahedral and these aluminum octahedral, and that really determines the alignment and arrangement of these sheets, if it's 1 octahedral to 1 tetrahedral, or if it's 1 tetrahedral to 1 octahedral to 1 tetrahedral. So 1-to-1, these two different types, or 1 to 2-to-1, or sorry, these 2-to-1. So there's, for every 1 octahedral, there's 2 tetrahedrals. Okay, so anyways, that is really kind of what we're talking about and thinking about. You'll hear, kind of in the soil science literature, or even in practitioners talking about, oh, those are mostly 1-to-1 clays, or these are 2-to-1 clays, and this is really what they're talking about. And a lot of this is dictated by the type of mineral and the weathering of that mineral in the formation of that soil. Okay, so if we think about this, I told you before that 1-to-1 clays can have a lot lower exchange capacity than these 2-to-1 clays. Okay, and so why might that be? Well, it's primarily because of a process called isomorphic substitution. Again, another Soil Science 101 term. And all that means is over the course of millennia, right, weathering of these soils, on the orders of thousands of years, tens of thousands of years, and maybe even longer, hundreds of thousands of years, we have a lot of water moving through the profile, a lot of interactions of the ions that are in soil. And sometimes this silicon, this +4 silicon or +3 aluminum, gets substituted out with other cations, right? And so if one of these cations, a +2, +2, +3, or a +1, exchange for this +4 silicon or this +3 aluminum, at best, we're substituting the +3 iron, but at worst, we're losing actual plus charges, okay? And so the older a soil is, typically the more of this isomorphic substitution. That is a 1-to-1 substitution, but it's got actually a lesser charge. And that results in actually a net reduction of permanent charge in the soil, okay? So that's really kind of what we're talking about. And this is just like, this isn't information that you're going to use every day, but it's just a good foundation to kind of understand what people are talking about with CEC, 2-to-1 clays, 1-to-1 clays. There's a process, and a lot of this is determined not by our management and what we do, but it's determined by how young those soils are, how recently glaciated, how, it all goes into kind of all the soils in the Midwest, the Corn Belt, are really fertile soils. You get down to Alabama, Mississippi, Georgia, and those soils aren't nearly as fertile. Well, why is that? What does that mean? Well, part of that is because of these mechanisms right here. Okay. All right, so let's kind of come back to the surface here. Think about organic matter. I mentioned that organic matter greatly influences. We already talked about, we'll talk a lot more about this as the course progresses. Organic matter represents a small fraction of the total soil, but again, plays a very disproportionate role, and it's certainly true with ion exchange and CEC. So a small amount of organic matter, if you go from 2 to 4% organic matter in a soil, or from 4 to 6 or something, you can increase your CEC greatly because of that. So it really increases the amount of exchange sites, the ability of that soil to hold nutrients, and that's why building organic matter is such a key piece of building a soil's fertility. And so there's these carboxyl and phenol groups, all kinds of stuff. These are the common ones, carboxyl groups and phenolic groups, that are able to, they disassociate with hydrogen, and then it leaves this negative charge. So then, say calcium or potassium, magnesium, something comes and attaches here, and then that is essentially a ion, a nutrient that is able to be plant available. Okay, so this is again a couple of the mechanisms with organic matter. Anytime we talk about organic matter, we need to realize it's incredibly chemically complex, and it's very difficult to kind of generalize across this. But here are two commonly occurring organic compounds, organic groups, this carboxyl group and this phenolic group that exist. Okay. Roots are made up of organic matter, and as such, they play, again, a disproportionate role in ion exchange and CEC. And so, these monocotyledons like grasses are typically a little, grasses often have much more root mass, a lot of fibrous kind of roots, but because of that, or partially because of that, they contribute maybe a little bit less to the CEC than things like dicots, like broadleaves, legumes, etc. So you can see the magnitude of CEC contribution, 10 to 30 versus 40 to 100. Okay, and again, not surprisingly, organic matter is primarily derived from root sources, from plant material, and so these are the same kind of exchange properties, the same types of organic compounds that are contributing in organic matter as in live roots. Okay. Buffering capacity is another concept. We don't really measure this like in a soil test, for example. There's ways to do that, but it's not commonly done. But it's more as a concept that represents the ability or capacity of a soil to resupply an ion. So in the last lecture, we talked about plucking nutrients out of that soil solution. Buffering capacity is a concept that describes the ability of that soil to resupply that soil solution with the ion that was taken up by the crop, or lost via leaching, or lost via atmospheric losses, or what have you. Okay, so it's often thought of in regards to pH. So how when we talk about buffering, it's the ability to resist changes, and pH and is an important piece of this. But we can think of buffering capacity in the context of pH and acidity. We can think of it in the context of nutrient supply. But both times, in both scenarios, buffering capacity of a soil will increase as CEC and organic matter increase. Okay, so at this point, you could ask the question, well, the more CEC I have, the more organic matter I have, it must mean it's a better soil, right? And typically, the answer to that question is a little bit tricky. It depends a bit, but as your CEC increases, your clay content will often increase, and you can get into really heavy clays that wouldn't be considered the most fertile soil of all time. So there's caveats, with this. But anyways, buffering capacity again is an important concept to think about. When we do something to the soil, if we're influencing the pH or influencing nutrient availability, what is the ability of that soil to resist to that change? Okay, so in some ways we can think about soil resiliency and buffering capacity in kind of a similar way, although those two things are certainly not the same. Okay. Cations have different adsorption strengths, and what does that mean? So the ability of an ion to essentially stick to the soil, it's how you can think about it. We've got a negative site on a clay surface. How does that clay prioritize who's on the VIP list or who's not? Of course, it's not really prioritizing per se, but it has to do with the chemical properties and the absorption strength. So aluminum has a very strong absorption strength, followed by hydrogen, by calcium, magnesium, potassium, and which is similar to ammonium, and then sodium is the least along the line. And you can see, as a general rule, as we go down this gradient of strongest adsorption strengths to the least strong, our valence, or our number of charges, essentially changes from +3 to +2 to +1. The difference, however, is the outlier here is this highlighted in red, this hydrogen. And hydrogen is different because it's got a very small hydrated radius, okay? And so the size of that hydration radius, i.e., the physical space that that ion occupies when it's in water, depends on the atomic properties of each one of these ions. And so for hydrogen, it's very small, and so because of that, it's held very tightly. Okay, and so something like sodium has a very, very large hydration radius. And so that's why sodium is held so weakly to the exchange site. So this slide is really just to kind of show that ions, or at least to relay that ions aren't held in the same regard, or they don't all stick to the soil at the exact same strength, or the stickiness. You can think about it like a magnet. The strength of the magnet is not, some magnets are weak, some are strong. Well, here are the strong magnets, and here are the weak magnets down here, okay? So in some ways, that helps determine how much of the ion is on an exchange site at any given time. However, it's more complicated than that, not surprisingly. We talk about this concept of mass action can remove more strongly adsorbed ions, and so in the context, we look at this and we say, oh, well, aluminum and hydrogen, these are both acidic cations. And so that's bad because that's going to drive our pH of our soil down tremendously. Well, the good news is that if we lime a soil, if we add a bunch of calcium on it, we can, by kind of the sheer numbers, flow off or remove, exchange calcium for aluminum, calcium for hydrogen, because of this idea of this mass action. It's flowing these cations off the exchange site. So if we lime, we're adding a lot of calcium, and that helps alleviate. It raises the pH, helps alleviate some of the drop in pH from these acidic cations. Okay, so there's a number of pieces that are going into what cations actually physically exist on those exchange sites, and what determines if they stick around or if they're actually leached out or moved off, or immobilized, or like moved into the soil solution, for example. Okay, base saturation is defined as the percentage of total CEC occupied by calcium, magnesium, potassium, and sodium. What's special about these four cations? Well, these are called base cations or basic cations because they drive the pH of soil up. We have acidic cations, things like hydrogen and aluminum, things like iron, for example, manganese, that drive the pH of that soil down. So they make it essentially more acidic. So base saturation is highly related to the pH of the soil. As our base cation increase in the soil, our soil pH by default increases. That's just shown here. Okay. And talking about how do we actually measure or quantify CEC, well, there's two different ways that it's done, two main approaches. Okay, so the most common way is to really estimate it. It's a simple and rapid technique, and it's really summation of the cations. So you're actually adding up the cations, and I'm going to post another video that's kind of going to dive a little bit deeper into that. And then there's a second way that is not done very often, at least in the commercial setting. It's really done in soil research labs or whatever, but it is far more accurate, and sometimes, not all the time, but sometimes this estimating CEC by summing cations will fall apart depending on the soil or depending on the pH or the situation. But the kind of the gold standard way to quantify CEC is this done in a commercial lab where we're taking ammonium acetate and we flood the soil with ammonium. It displaces all the cations, and then we take, in a second step, we flood the soil with this barium chloride, and it displaces all the ammonium, and then we quantify the ammonium. So it's basically like physically removing, all the cations except for ammonium, and then we're quantifying ammonium. So this is, anyways, there's a little bit more about this in soils textbooks, or you can, references online, but this is not a test that's done that commonly except for maybe in a soil characterization lab. This sum of cations is much more common. So again, we'll wrap up here, and then I'll post another video going a little bit deeper into that.